Hello, good afternoon. Name is Eddy Yap. I'm with Dow Chemical for over 25 years. Been with the Olefins and Aromatics and Alternatives Tech Center there as the technology director for automation, digital, and also with IP protection. I'm sure most of you have seen this before, some sorts of it, some variants of it there. I really like this because it really helps translate the digital transformation activities we have into business value, right? We start at the bottom, obviously, with the data that we have there. We have some models, we know how to manipulate the data itself there to give us some insights into the system, give us information. Then you bring our SMEs on board there to help make sense out of those insights out of the data, right? And once you come back with the recommendations, we work with the teams to see how do we put this into action itself. I think the most important part there is to close that loop because all these activities that you do without making any changes into the plant or into the process itself there, we're not capturing the business value. And this could be what you do in the field, like having the operator make changes in the field, or you have automated set points from your advanced control system, or it could be a real-time artificial intelligence system there that we have. This is just a simple roadmap of what the things that we have today and how to kind of pull it together into what I eventually call truly an AI kind of process system there, right? I'll cover a little bit of this in the next slides there. So it's not a blog post movie, but I just came across this movie on the flight south there and thought it was, the concept that they mentioned here really resonates with what we are doing in this space here, right? And the designer of the game, Kazunori Hamachi, is out there. Now, this is a game back in 1997. It's a long series of games there, right? So when he designed the game itself, that he wanted to be as realistic as possible. So they went through years of just capturing details, the specs of the cars, the racetracks, the performance there, but all that, and build into not just a game, but really a racing simulator on that front. So I thought that was pretty interesting, and see how they kind of connect with what the things that we're doing today. So, well, to win the race, you need to make sure you build the best race car you have, right? But in the real world, we can't afford to update all our crackers or our fleet to the best they can there. So what we can do is really know the components that we have, right? Pick the right components, know how they work itself there, know how to configure them, and make sure that you keep track of what I guess the key parameters that you need to care for in this system. For example, you have vortex meters, they're really susceptible to fluid density changes. Make sure you include that as part of your monitoring system, your calculations. We don't control steam drum level just by the raw measurements. We compensate for it based on pressures, temperatures, because we know it doesn't work through the whole operating phase, right? So those are the things about knowing your system itself, knowing your components, knowing what they can do for you itself, and making the best out of them itself. What we look at, the first part is really to make sure you, especially in a real-time system, is signal processing. I come from automation world, and we know that if an instrument fails, a valve fails, it could mean equipment fails or trips itself, and then you end up with a facility that comes down with it, right? So being able to process the signals carefully, making sure they look at all the different aspects of it, including maybe even the frequency spectrum. Is the noise ratio changing on that front? Maybe that gives a little hint about things that could have changed or impact the system, right? So once you know that the instruments are good, you trust them itself there, then you can start to build some more insights into the measurements. Like pressures, flows, maybe they usually go together itself there. Build the correlations itself. You have valves, you have valve estimators that you can use. You can have sensors in the system. You can actually start to predict a lot of the components that you see in the pipes there. You have to analyze in the system. You can start to extrapolate that, right? So that kind of information needs to be built into your system so that you can give more information to the folks that are using this. And the most important part is prepare for the worst. Instruments lie. It's not because they intend to lie. It's just that they're installed the way it is. There's ambient effects that happen into the system. There's age that comes into the system. So you need to be prepared for that. The valves do fail. I mean, we've seen that, every month in the facilities that you have there. Some better, some worse. So we need to make sure that we are building the system to be robust for this kind of situations. When they, how should I put this on here? So when I look at the movie itself, then they shoot these racing lines. I thought that really matches well with what we have in our system today, right? We have, over the last 20 years, we've implemented advanced control and optimization. Those are all based on first principle systems that models that we have built over time, right? And with that, you have optimum lines of where best place to go, follow those set points on those. So those are racing lines, I will call them there. You let the system approach those lines. But with hydrocarbons processing, it's a very deterministic, I call it, because we know how the process works. We've got tools from Aspen, steady-state models, CFD, FlareNet, HDRI. All those are all the tools that you can really use to kind of make sure that the data that you see today really matches what in theory itself there, right? And the difference between those calculated models or the theoretical models is that it doesn't have all this dynamic information with it. It doesn't have all the ambient effects that goes in the system. So when you have like a real-time optimization results and then you have actual run data, sometimes that's a mismatch, right? So what you can see, like on here, you have what they call the red racing line, but what if you have a system that is supply constrained or demand constrained itself there? You need to adjust it, and that racing line will change depending on the situation you have there. So that's what I'm trying to say on here is that now we've got years and years of such optimum operating points on there for our old facility itself there. Those are data that we can use as part of our machine learning on those ones. So that's what we built our time series data based on all this information. Like a real-time optimizer output has like 150,000 variables that it calculates every hour. We measure 10,000 signals, but there's 150,000 variables that's being calculated every hour, right? And you put that against the time series, against all the scenarios that you've been running. Now you have a big picture profile of all the things that you can do with the data that you have on the system. So find the optimum line, challenge that line, make sure that you understand why it is there, why it's working, and then close the gap in the system. We've been working with cars since 2011. They built high fidelity simulators for us itself. We've been working with them to build, at least for since maybe maybe 5 ethylene crackers that we have so far, and about 8 different kinds of furnaces that we have there. One thing is that their platform is based on first principles chemical engineering. So we trust the results that come out of that on the system itself. Now you build in together with DCS configuration logic. We use a lot of state-based control, so that's very complicated logic. So we bring that together and then we test it to make sure that our logic works, but also to train our operators on how it works, what it looks like. This thing runs anywhere from 1 to 10 seconds. So we've got steady-state simulators that run every hour or so. We've got dynamic simulation systems that run every 1 to 10 seconds itself there. So you give us a different set of data now. You can start to look at transients, the transitions, how it works on this system. And behind the scenes, you can actually look at what's happening on each tray, what's flowing in the pipe, right? So that brings additional insights that we have into the system, right? So that's what we're trying to use over here on kind of build the baseline, builds the dynamics to compare against that. And with that, you can see the difference, right, on between what's actual, what's being measured, what's in the optimum line, and you can start to analyze the data on there, see what's different, where the gaps are that we have. Now, from my opinion, a real-time artificial intelligence system needs to be able to take a look at the data, make the right decisions based on the expert opinion. That's why I put on the top there, you need your SMEs to come in, you need your best practices to come in, you need the operating procedures to come in. make sure that it's validated in the right manner itself, and it needs to give you a good response, the right response in a consistent manner. Now, in our business, we cannot afford a mistake on here because that's a very big process safety consequence that goes with that. So we're not all there yet. We're still working on some of the pieces that we have here. It's like Colin mentioned that this is an evolution, not a revolution for us for now. Thank you.